Hello ladies and gentlemen, welcome to chemical bonds. And so with this video today we're going to talk about ionic and covalent bonds, and then polyatomic ions and transition metals and how to do some of those naming. I'm going to do a little bit of review first before we hop into it too much. And so the first thing that we've actually done, or what we did last week, was we looked at valence electrons, and that how the first column of the periodic table, let me find my pen right here, maybe all these right here, let's go with a little bit thicker on that line there. All these that have one valence electron make a +1 charge. On this second grouping right here make a +2, and then we have a +3 here. Now for right now we're going to skip this fourth row right here, and we're not going to do much with it in this unit. Instead we'll look at what happens when we have 5 valence electrons, and that gives that that -3, -2, and -1 charges that these atoms or these elements particularly tend to form. And so we're going to have that kind of in our back pocket when I'm looking at ionic bonds and covalent bonds, and we're going to be looking at what do these charges represent and how does this play into chemical bonds. Another thing we're going to put into consideration is electronegativity. And so what you have is that, as just a nice reminder, is that fluorine is the most electronegative atom. It's really selfish. It just wants to rip electrons off of other compounds. And then cesium, for example, is a really selfless. It doesn't want that electron. It only has one in its valence shell. It has a lot of shells beneath it that are full. And so that's why as we go down on the periodic table, we see that our electronegativity also goes down. So with those two things kind of in mind, we can now look at bonds. Now, we're only going to cover two types of bonds here. We're only going to cover ionic and covalent bonds, and then what we can do with those. So what we got here is we got ionic bonds. They tend to be weaker. And the reason they tend to be weaker is because they kind of work like a magnet. They have a positive and a negative side. And I'm going to unpack that a little bit more here in a second. But the one thing I want you to do always when you're trying to figure out what kind of bonds are being formed, you have to look at the elements involved. And so an ionic bond is always going to be a nonmetal to a metal. So if we look at our periodic table, I'm going to use this one for example. If we find a metal, which is this side of the periodic table, this whole left side, bonding with a nonmetal, kind of this right side, if we're going across the periodic table, it would then be an ionic bond. The only caveat here is if you remember that hydrogen is a special guy, and he actually belongs with the nonmetals over here. And so hydrogen being a nonmetal is kind of the one little tricky part there, but we'll get there when we get there. Okay, so let's go back to this. So ionic bonds are nonmetals to metals. Covalent bonds, however, they tend to be higher in energy because the bonds between them are stronger. How the electrons are being pulled are a little bit differently. And then that's all going to be a nonmetal to a nonmetal. And so examples of ionic bonds could be something you've already know, which is NaCl. That's table salt or sodium chloride. And then what's another one? So lithium fluoride, LiF. We're going to talk about these namings of these ionic compounds. But what we notice is that for sodium is a metal, chlorine is a nonmetal. Lithium being a metal, fluorine being a nonmetal. So we got metal, we got nonmetal. Let's do nonmetal and metal. And so we can see that these would be ionic bonds. Covalent bonds, however, kind of like H2O. Well, we can know is that good old-fashioned water. And this is a nonmetal bonded to a nonmetal. So the very first thing I want you to do when you're looking at any sort of compound in this unit is to look at what are the two elements involved. And from there we can predict what kind of bond it is. So let's unpack that a little bit. And so when we look at bonding types, back to that ionic bond, if we look at sodium, sodium really likes to form that +1 charge because it's in that first group of the periodic table, which means it only has one valence electron that it would love to give away. And it happens to be close to a neighbor here That's chlorine, and chlorine loves to take, and so that would then make a perfect pair there. We have one electron willing to go away, one willing to be sucked up, and so what we get here is you get this little bond. Now, some people then ask the question, well, where's the bond at? How does this play into a role? Well, what we find ourselves is that since sodium has a plus charge now, and that chlorine has a minus charge, they kind of work like magnets. It's a magnetic pull. And so we've got a plus side right here and a minus side right here, and they kind of just snap in close together with this bond right here. And so when those two happen, it makes a wonderful, delicious thing we put on our table, which is sodium chloride. That's table salt. And the reason that this bond is so weak is because there is no sharing of electrons here. The only thing holding these two together is this kind of electromagnetic force where the electrons cause the charges, and so they're kind of stuck like magnets. So any ionic bond, or most ionic bonds, you tend to put in water, and water will actually just chop those bonds in half, and that's why salt can dissolve so easily in water, is that it can separate those two atoms from each other and then just make it easy to dissolve water. Okay, so now what are we going to do with this? What we're going to do is we're going to be able to predict what kind of compound we have and be able to name it. So the first thing I want you to do is, get in the habit of the first step, would be to list the elements in your compound. So for example, if I had LiF here, you'd find Li on the periodic table, and that would be lithium. And then you'd find fluorine, and you just write those two out, lithium and fluorine. And then what we're going to do is we're going to remove the suffix ending from the nonmetal. So you're actually not going to touch the lithium part at all. And so I'm going to write that just a little bit better. And then fluorine, we are going to cut off that ending. So the endings you can chop off are YGEN, INE, ORUS, and GEN. So the endings of those elements we're going to chop off and replace with IDE. So lithium fluorine becomes lithium fluoride. Okay. Now one thing, I'm going to pull up my periodic table. I have it on the other screen here. You can't see it. Yes. Okay. That way, when I reference my periodic table, mine's right here, but you can't quite see it. It's on this other screen. Okay, so let's continue on. Let's move on, or at least unpack this a little bit more first. Here we go. Okay, there we go. When we look at ionic compounds, we have a metal and a nonmetal, so we got lithium and fluorine. And these two compounds with ionics, there's only one ratio for these elements to show up, and that's a 1-to-1 ratio here. Because lithium makes a +1 charge, fluorine makes a -1 charge. The problem you run into is prefixes can get confusing when you look at down scope on some things. But if we know it's ionic, there's going to be no prefixes. So as a hint for kind of covalent stuff, carbon monoxide, carbon dioxide, you have these prefixes which, because those elements can show up in a bunch of different varieties, but lithium and fluorine can only show up in one way. And so if these two elements are together, they're always going to be a 1-to-1 ratio, which means there's no special naming. And the last thing we're going to say is ide also means one element typically. And so this is lithium fluoride, meaning it's only composed of lithium and fluorine atoms. Nothing else is kind of mixed in. This will make a little bit more sense when we unpack polyatomics and more on those covalents. So as we go on, hopefully this makes more sense. What I want you to do now is go ahead and hit pause on this video and try to predict the molecule that is going to form here. So here's the first thing I want you to do. For lithium and fluorine, for example, I want you to write the two charges that those would make using your periodic table. And so back onto looking at those valence electrons, you should be able to predict those charges those would make. Then what I want you to do is kind of figure out what is going on here. Well, lithium and fluorine, since it's a +1, -1, those charges will actually cancel out. And now we can name this as lithium fluoride, just like we did before. Okay? But what I want you to do now is I want you to try magnesium and oxygen. Hit pause on the video, see if you can help figure out what magnesium and oxygen are going to produce as far as when it comes to the naming of them. Okay, I'm going to try it out now. Magnesium and oxygen. Let's go ahead on top of that. Let's erase this real quick. On top of that, I'm going to predict the compound that will be formed. So we got magnesium, which makes a +2 charge. You have oxygen, which makes a -2 charge. The 2 electrons that magnesium is willing to give is going to be equal to the 2 electrons oxygen wants. So when these 2 elements come together, those are going to cancel out. As a big hint, kind of the next 2 examples won't cancel out. And then we can just name this as magnesium oxide. Where did the oxide come from? Well, oxygen. Well, you're going to chop off that ending, that YGE ending, and add IDE. Okay? So let's do these next 2 ones rather quickly. That way this video is not going to be super long. Alright, sodium and phosphorus. So sodium makes a +1 charge. Phosphorus, however, makes a -3. Again, if you have a hard time with this, you need to take a backtrack, look at valence electrons, looking at your periodic table. When these come together, however, sodium is willing to give 1 electron, but phosphorus wants 3. So how do we counteract this? Well, that means if we have a second sodium ion here, that means now we have 2, but we need 3. So in order to cancel this out, we would need 3 sodiums to show up to the party to cancel out the -3 on the phosphorus. So what is another way to think about this? And this is kind of the shorthand example, or the way I would recommend students doing this. When you're writing ionic compounds and they don't cancel out, go ahead and just write the 2 elements you have, but then take this number, not the charge with it, just this number, and take it on down here. And what we find ourselves in is that these numbers allow us to predict how many of each is needed. So, but there's one little small caveat here, is that scientists love to be lazy. And so what they do is they don't write this 1. So if you ever have, when it comes to writing a chemical formula out, you see you writing a 1, just go ahead and just erase it, scratch it out, don't need it. Scientists love to be lazy, or efficient in better terms, in writing their chemical structures out. So this Na3P would be the appropriate writing of that compound. What we're going to do now is we're going to name it. So sodium and phosphorus becomes sodium, because you don't change that first element at all, and phosphorus becomes phosphide. Sodium phosphide. And that's because you take the phosphorus ending, you chop off the end, and then add IDE. And there you go. Okay, what I want you to do now is kind of hit pause in the video again and try boron again, boron and oxygen on your own, and see if you can follow along with me, or at least try to figure it out. But I'm going to go ahead and get started. So boron makes a +3 charge. And so let me pull up my periodic table to make sure we are following along here. So I got my periodic table right here. We see boron is in the 3rd column right here. It makes, the 13th group, but the 3rd column, ignoring the transition metals, and that gives us a +3 charge. Oxygen is going to be a -2. So when these come together, we are going to crisscross just like we did before. You got boron, we have oxygen. This 2 is going to come down here. This 3 is going to come down here. Oh. Well, U-turn there. There we go. So we got B2O3, and this would be boron oxide. Okay, ladies and gentlemen, there we go. We are rolling when it comes to figuring this out. Okay, let's move on forward and kind of what could we do the other direction? So if I give you, you should be able to do now is naming, if I give you a compound. What I also want you to be able to do now is if I give you the compound, you can then, or should I give you the name, you can then give me the compound. So potassium chloride, here's a recommendation on trying to figure out how to name these examples. You might be able to get to it pretty quick with just looking at what you have. So lithium and fluorine makes lithium fluoride. Sodium and chlorine makes sodium chloride. Beryllium and oxygen makes beryllium. I always like to spell beryllium wrong. Where is it at? The B-E-R-Y. I think I like to spell it with 1 L instead of 2. Beryllium oxide. Okay, and so all we did here was just write the first element, take this element, second element, chop off the ending, and add IDE. Okay, now let's go the other way with it. Let's given the name, let's now be able to write out the formula. And this is going to be kind of a tricky thing because what I see some students just fall into is they just find the 2 elements and then sometimes they're right, sometimes they're wrong, and the problem is that you have to look at the charges. We don't know, looking at potassium and chlorine, magnesium and nitrogen, calcium and oxygen, if those all show up in a 1-to-1 ratio. So what we have to do then is instead also look at the charges. So potassium makes a +1. Chlorine, however, would make a -1. That's a 1-to-1 ratio. This would cancel out to KCl. Magnesium, however, makes a +2. Nitrogen makes a -3. These don't cancel out, so we have to do a little bit of that crisscross method of Mg3 and 2. 2 goes down here. 3 goes right in here. Okay. What about this last one? Calcium oxide. So calcium makes a +2 charge. Oxygen makes a -2. +2 -2 cancels out. You get CaO. Okay. So there you go, ladies and gentlemen. What we've done is just done a couple of practice problems dealing with ionic compounds. Let's continue. Let's switch the gears a little bit. And now let's look at covalent bonds. The problem with covalent bonds is that if we think back to the electronegativity that we talked about at the very beginning, if fluorine really wants electrons, it has no problem ripping away electrons from weak stuff. But the problem is that what if it's close to itself? So what if, fluorine got in a fight with itself or was trying to rip away electrons from only itself? Well, the thing you get going on is that instead of one side giving or taking electrons, you have a sharing of electrons here. In that these electrons kind of bounce back and forth and they're locked in position. You can kind of think of it as ionic compounds, kind of like a middle schooler versus a college football player. Who's going to win? Absolutely a college football player because he's a lot stronger. However, if we have 2 college football players kind of fighting against each other, which one's going to win? Well, it's going to be a much more even struggle. And since there's a lot more tension involved, there's going to be a stronger bond, kind of a stronger interaction. So since these electrons are shared, there's more energy stored up, which means that they're, instead of bouncing back and forth, they're kind of just chilling in the middle. Okay. So let's kind of look at what can we do then with covalent bonds. We're going to follow the exact same steps of 1 through 3 on naming ionic compounds, We're going to list the elements, metal and non-metal, but we're going to have to tweak that though because now we have non-metal and non-metal. Then we're going to take off the ending, add IDE, but this time what we're going to do is we're going to include prefixes. And the reason we need to include prefixes is because some of these combinations of elements, like carbon and oxygen, can pop up into a couple of different variations. So CO is carbon, but it only has one oxygen. So we're going to throw this prefix in front of it and call it monoxide. CO2, that's going to be carbon again, but that's going to be dioxide. And why is that? Well, we're still going to chop off the endings and add IDE, but now we also need to include how many of them there are. So mono being 1, di being 2. And so what I recommend you do is when you write this down, kind of have it off to the side or close on your periodic table, that these prefixes will help when naming covalent compounds only. Again, that's just a non-metal to a non-metal. So let's look at some of these other examples and what we're going to be able to do with them. CH4. Well, C being carbon. Now we have to look at this 4. So what's the prefix for 4? And that would be tetra. And let's just write here is tetra. Carbon, tetra, hydrogen. Well, if we look at hydrogen, we're going to chop off that ending of OGEN and add IDE. So carbon tetrahydride. Oh, I also fix that again. Spelling error there. There we go. Carbon tetrahydride. Okay. If you look up and you were to Google some of these things, you're going to find out that some of these compounds follow different naming patterns. And we're not going to go unpack those a little bit, but carbon tetrahydride is more known as methane. And that's because this falls under a class of compounds called organic compounds. We're not going to talk about those at all, but I do want you to be aware of the fact that since we're not doing this method of naming, be careful when you're doing your research on the type of compounds you're forming, or at least doing your homework. Okay, so nitrogen, for the second one, NO, is going to be the same. We have nitrogen, and then we have one oxygen. So that's mon. Instead of oxygen, we're going to chop off that ending and add IDE. Now, usually at this point, students like to ask the question, hold up. Why don't we say mononitrogen monoxide? And that's because scientists, like I said, love to be efficient. A lot of these covalent compounds, the first element tends to be a 1 already, unless different, so it can be assumed to be a 1. If it's assumed to be a 1, we don't have to write anything in front of it. So you're never going to put mono as your very first element. Okay. Now let's do the other one again. We got NO2 was nitrogen monoxide. NO. Let's do NO2 now. And this would be nitrogen. Instead of mon, the prefix is going to be dioxide. Okay. Now, there is another thing I want to talk about just a little bit is the prefix for 1 is mono. And so I do see some students putting in double O's. When the first letter of that second element is a vowel, you tend to chop off or there's no repeats. And so what we do is we just, instead of putting 2 O's, we just put 1. Okay. Alrighty, and let's look at, can we go the other direction with this? Now, the really cool thing and the helpful thing when naming covalent compounds is it tells you how many's there. All you have to do is write out the compound. So we look for silicon, for example. Silicon's Si. There's no prefix in front of it. So that means it's just one. We have dioxide, which means we have O2. Silicon dioxide is just some good old sand. Okay. And let's just continue on with the last two examples. We have carbon monoxide. Well, carbon is just going to be C, and then mono meaning one, we have CO for carbon monoxide. There is a classification of chemicals called diatomics, and so what I'm going to do is I'm actually going to take just a quick little sidebar conversation and talk about the diatomics. We have these certain elements that love to show up with themselves, and those are hydrogen. So anytime you see hydrogen by itself, it's actually hydrogen 2. The same thing with, we have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. All of these elements are called the diatomics. Di being 2, atomics being atom. So these are 2 atoms in the molecule. So anytime you see or create any of these elements by themselves, they are automatically going to bind with another one of their neighbors and to be nice, happy, and stable. So anytime we see chlorine gas by itself, it's not just Cl, but it's also going to be Cl2. That could be the same thing with hydrogen gas, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. All of those, when they're by themselves, form a nice little pair. I have heard this called the Brinkelhoff elements, but I digress. Okay, what I'm going to do now is I'm going to put a pause in this video, and we're going to leave this here for now, and then we're going to pick up with this in class with polyatomics and what we can do from here. You will need your polyatomic list in hand, and then we'll be able to move forward as a class. Good luck. If you have any questions, let me know, and I'll see you guys hopefully tomorrow. Take care.